Good morning, students, friends. Today we are going to learn another the important and a very familiar instrument, that is moving iron instruments. This instrument can be used in case of DC as well as AC. This instrument has so many characteristics, and it has an accurate and cheap and best and a simple in construction comparing to moving coil instrument, which has already learned in previous class, where the moving coil instrument can be used only for a DC. At the same time, cost is more. Then let us see one by one in detail. So, this topic regarding to third semester C18 scheme EE 304 electrical and electronics measuring instrument subject, that is attraction type and repulsion type of MI instruments. In previous classes, we have seen the construction and working of moving coil instruments, advantages and disadvantages of moving coil instrument, the application of moving coil instrument, errors and their remedies in moving coil instruments we have seen. At the same time, how PMMC, permanent magnet moving coil instrument, enhance its range from some milliamperes to hundreds of amperes by using shunt and multipliers. As we know that this moving coil instrument consumes, while taking the reading, is only less than 200 microwatts. Burden on the circuit is very less, but it is limited to manufactured with coil 100 milliamperes only for in case of ammeters, and it can be used for measurement of high range with the help of low resistance material, that is magnetic material, for as a shunt. In case of AC, we are going to use constant as a shunt material to enhance this MI type instruments. We can see later. Now, in your syllabus, so we have seen the PMMC meter has a voltmeter, PMMC meter as a ammeter, how to connect in real time circuits, and what are the unknown shunt resistance and multiplier resistance, that is the series resistance, how to measure that value, and how these instruments can measure the value with help of shunt and multipliers. Last class we have seen with examples of problems, and there is a two problems in your syllabus that I think you have done that thing. Very simple. Put the formula, get the answer, you are going to get it. What are those problems? So let us recall once again. Here the PMC meter, one problem is given. What he has given? A permanent magnet moving coil altimeter. For example, I am going to write it only. Here permanent magnet moving coil altimeter has a resistance of 10 ohms. So here, so let us assume this is a 1 voltmeter, has meter resistance Rm is equal to how much? 10 ohms is given, because and a full scale deflection is reached when a potential difference of 150 millivolts is applied across the terminals. That means here the Vm meter mag full scale reading is given, that is equal to how much? Is 150 millivolts, 150 millivolts that can be measured, okay, millivolts, 150 into 10 to the power of -3 volts, it can full scale deflection. Full stop. The area of the moving coil is A is given. What is the A? Area of the coil is given, that is equal 6 into 10 to the power of -4 meter square is given. And there are 40 tons, N is given, 40 tons is given, okay. The torque provided by the spring is, okay, here is a TC is given, the spring control torque spring is given, how much? So 0.4 gram centimeters. So better to convert into kg meters, okay. So because we are given the meter square area, so here also, so we convert into kg per meter square. So by simple, the grams to kilograms and centimeters to meters, you convert it, you know that thing. That is, we are going to get what's the value? So we are going to that 0.4 into 10 to the power of -5 Newton meter kg per meters, that is the value, okay. Now what is given? At full scale deflection, calculate the flux density in the gap. He is asking what is the B value, okay. Once again I will read once again problem, you can see it. A permanent magnet moving coil altimeter has a resistance of 10 ohms and full scale deflection is reached when a PD of 150 millivolts is applied across the terminals. The area of the moving coil is 6 into 10 to the power of -4 meters square and there are 40 tons on it. The torque provided by the spring is 0.4 gram centimeters at full scale deflection. Full stop. Calculate the flux density in the gap. So here we are going to find the what is the B. As we know that the fundamental already we learned that the number of equations, the deflecting torque produced in moving coil instrument, the well known is equal, what is the formula? Here the deflecting torque TD is equal to the formula, just you write it, that is equal B flux density, current, area and number of turns. So this is the basic formula. But now here you can see, here TD is not given, N is given, area is given, current is not given but indirectly is given, and flux density we are going to find it, okay. Now you can see, now TD is not given but indirectly is given. What is the condition? So under standstill condition, the TD is equal to TC when in the equilibrium position. So TC is given, so this TC is given, that is why TD can easily, that is 0.4 into 10 to the power minus 5. We know that. Now, I required here. So, here indirectly the meter resistance voltage is given. Apply the Ohm's law. That is equal to I is equal to, we are going to get, what is the value? I is equal to V by R. So, V is equal to 150 millivolts divided by 10 ohms. So, thereby I am going to get current is equal to, I value is equal to, I am going to get simplification. So, 0.015 amperes. Now, you can see it. By knowing the all values here, TD I known. So, TD is equal to TC, that is equal to, that is a 0.4 into 10 to the power minus 1, TD is we known. Now, I known, I is equal to, we calculated 0.015 amperes. Now, area directly is given, thank God, and N is directly given, thank God, the N is 40 tons. Simply, N is known, A is known, I is known, TD is known, only B is unknown. Just you calculate the B is equal to TD by I into A into N. Then we are going to calculate that value. So, we are going to get the B, that value should be, so that is equal to, after simplification we are going to get it 0.109 Tesla, the Webers per meter square. This is the answer. Dear friends, once again I am going to explain it. Here simple formula, that is a TD is equal to B into I into A into N. Previous classes we have this formula we known. Now here TD is equal to TC under equilibrium condition. So, TC is given, indirectly is given. Now, here B is not known, we are going to find it, and I is given indirectly. So, by applying the Ohm's law, the maximum deflection is the 150 millivolts divided by 10 ohms, we are going to get the current. Now, area is directly is given and N is directly is given. Simple substitution of these values, we are going to get unknown value, that B is equal to 0.109 Webers per meter square. This is the one problem. You try at home. Okay. So, remaining problem also very easy. So, you do it. Okay. These are the simple problems. Now, let us come to our topic, that is equal to the object. On completion of this period, you would be able to know the construction of moving iron attraction type instrument, the principle of operation of moving iron attraction type instrument, advantages and disadvantages of moving iron type instruments. Similarly, the construction of moving iron repulsion type instrument, the principal operation of moving iron repulsion type instruments, and same, that is the advantages, disadvantages of the repulsion type instruments we are going to see. Okay. So, we are going to see one by one. Now, before known to unknown, let us see what we have known and what we are going to unknown. We link each other, then we are going to understand easily. How do magnetic poles attract each other? So, in school level we have seen magnet, permanent magnets, electromagnets. Any magnetic material behaves as a magnet, one side acts as a north pole and another side as a south pole. Now, as per the laws, famous laws, the similar poles, like poles repel each other and opposite poles attract each other. So, we have studied in school levels. Same that principle we are going to apply here to application of our moving iron instruments. Now, according to the Coulombs law of magnetism, what is said? Unlike poles attract each other and like poles repel each other. You can see here is a U-shaped magnet. It has the two poles, north pole and south pole is differentiated with the colors. Let us assume red color is the one and blue color is the another pole. Now red color is the north pole and blue color is the south pole. Similarly, here another U-shaped magnets placed at that condition, then what is we are going to observe? The north pole of one magnet and south pole of another magnet, and vice versa. You can see it if kept nearby each other, automatically there is a strong electromagnetic field developed between the two poles that is try to attract each other, because north pole and south pole of different magnets try to attract. As well, our famous forefather Coulomb. This principle we are going to use it. If these poles, north pole and south pole placed, then repulsion takes place. That is the repulsion type instrument. If opposite pole, one north pole and south pole, in this condition, a north pole and south pole placed nearby each other, there is an attraction takes place. Based on this principle, we are going to manufacture, that is a attraction type moving iron instrument. If the instruments are now north pole and south pole placed nearby each other, there is a repulsion force between the magnets. That principle we are going to use in repulsion type moving instruments. These basic principles we are going to apply it in our moving iron instruments. Okay, let us see. Now you can see the attraction type. Here is the red color is the north pole and the green color is the south pole. A similar magnet is placed side by this one. Now south pole and north pole, there is a magnetic field between the two poles. We know that magnetic field and of one magnet and so another magnet in between, there is a dotted line, so you can observe it. What is happening? So due to the opposite polarity, unlike poles, they attract each other. In second case, you can see it here. This first case, you are going to attract each other because there are different poles. Now here second case, similar south pole and south pole, what will happen? Now automatically there is a repulsion force between the two magnets. So they will try to move away from each other. So you can see whether you are going to south pole or north pole, there is a repulsion force. Whereas in first case, the attraction, whether you are going to south pole or north pole south pole, the opposite polarity, unlike poles, attract each other and like poles repel each other. You can see here. Okay. Now here an example is given. So here in book, as you can see it, A and B are the two magnets considered are getting attracted, because here A magnet and B magnets and both are opposite polarity. Then there is a magnetic lines of forces here, at the same time magnetic lines of forces here going to. So that means here the north pole, this is the south pole, so lines of forces is flowing this direction. So this is known as a magnetic field. In between, if you are placing any type of the iron piece or magnet, then automatically there is a forces created. That force try to attract that iron piece towards north pole or south pole. Okay, this principle we are going to use in our instruments. So let us see. The above principle is utilized in attraction type and repulsion type moving type instruments, both. So let us see one. The instruments are two types. One is the attraction type, another is the repulsion type instruments. So attraction type are my instruments. So here you can see the two types instruments, and same attraction type instruments, how the physical present in laboratories. Here you can see the parts of the instruments. So you can see this is the fluid friction damping purpose, and this is a coil. You can see this is a coil in which there is placed the one iron piece in the oval shape, and this is the spindle. You can see side by figure also. Okay, these are the different parts. It has a electromagnetic coil, moving iron piece, you can see here the moving iron piece, magnetic coil, and this is the fluid friction damping, this is a spindle and jewelry bearings and the springs, and we are going to use the weights for the gravity control purpose. This is a pointer, this is the scale. These are the different parts. If you are observing in the plan, if you are seeing the top side, we are going to same thing. Here you can see this is the air friction damping. In this case, the fluid friction damping. And this is the coil. If you are seeing the cutter's coil, so you are going to the coil is this direction. Now, so this arrow mark, it is the shaped. This is known as the oval shaped iron piece, moving iron, which is linked to the attached to the spindle. You can see the spindle. Here is the iron piece, and top and bottom there is a provided the spring control here. So in this case, there is the weight control, gravity control. So here also they provided the balance weight. Okay, this is a one physical construction of attraction type moving iron instrument. We can see. Now, the construction of attraction type moving iron instruments. It consists of hollow cylinder coil or solenoid. We can say this is known as a solenoid. So previously we have seen cutted into portions. Now, a spindle is supported between the two jeweled bearings and is near to the coil. So here top and bottom we provided the jewelry bearings, jeweled bearings. The spindle is this one. A oval shaped soft iron, a pointer or attached to the spindle. So you can see the moving iron oval shape. Oval shape means this is the oval shape. Okay, not circular, oval shape. It's a pivoted here. It attached to the spindle. Then it will easily move this direction and this direction. That purpose we have the oval shaped iron piece. And this is attached to the spindle. And the top and bottom we are going to provide the springs, the controlling torque. Okay, now the oval shaped iron is freely to move inside the coil. So what you can see here, oval shape, you can see this is the oval shape. Moving iron in the oval shape, it is free to move inside the magnetic coil. The pointer moves on a graduated scale. You can see the pointer is moving on a graduated scale. Instrument is provided with a spring control. So here spring control is provided. Instrument is provided with the air friction damping. This is air friction damping. We can use the any type of the dampings. Here we use the air friction damping. Now working of attraction type instruments. When current passing through the coil, it magnetized. You can see in the figure. Now here this is a red color is the coil, copper coil, cut it in off sectional view. When that means here you can see it. This is a coil. Okay, when the current is passing through this one, there is a strong magnetic field developed inside the coil, solenoid. So this is a solenoid. Now this portion is I cutted in this portion. I am seeing this direction. So I am going to see, I am seeing this one. So this direction. So I am going to get it. When current is passing through the coil, what is happened? There is a strong magnetic field developed inside the coil. Here is the inside strong magnetic field developed. So due to this magnetic field, nearby is prey. Nearby is an iron piece is placed. The coil attracts the soft iron piece inside the coil due to the strong magnetic field. As the iron is attracted to the spindle also attached to the spindle, and the spindle also rotates. Once it is a mode, here what will happen? So, we place this one and it is attached to the spindle. Once this, here is a pointer replaced. Normal condition, it is a 0 condition. In second case, whenever the spindle is moved, that is instead of this place, it is moving this direction. It is moving this direction, attracted. Then automatically spindle will rotate and the pointer will move this direction. Okay. That means here what has happened? Initially the pointer is this is this shape. Then pointer is maybe this one or 0 condition. Once it is magnetized, it try to attract towards the inside the coil. Then it will comes to the iron piece will comes to the inside the magnet, and it is connected, it is contacted, it is attached to the spindle. The spindle will move in clockwise direction. Then which is the pointer is attached to the spindle, that will move from this position to this position. That means based on the attraction force, the pointer will move, that is the angle theta. If more force, more inside, more twisting, more movement, more angle may be provided. That means based on the current, if the current is minimum flux developed or minimum attraction towards the solenoid inside, the deflection is theta is the minimum. If more current, more angle. Okay, that's the basic. The pointer moves on a calibrated scale, which is indicate the strength of the current through the coil. Okay, so that is the basic principle. Now you can see here one good example given by the one scholar. Here what has happened? So here there is a solenoid. When the source supply is given to this one and solenoid nearby, nearby they placed one iron piece, and it is attached to the some spring mechanism, and it is with the one pointer is placed here. On this is a graduated scale. Simple understanding, but layman can easily understand this thing. Now what happened when there is no current? The iron piece is away here, there is no movement here because there is no magnetic field here. Now the spring tried to attract to one direction only. Now spring is in a stable position, no attraction, no repulsion. Now when the current is passing through this one, then we know that whenever a current passing through the coil, it establishes a strong magnetic field. This strong magnetic field, so what will happen? There is a magnetic lines of forces here in this area. Due to this magnetic field, so whatever the iron piece is placed inside the magnetic field, this iron piece forcefully becomes it is a electromagnet. The magnet becomes a magnet. Now due to the magnet, so it also this iron piece will try to attract towards the strong magnetic field inside the coil. So before that one, it cannot attract it. Once supply is current is flowing through this one, it establishes the electromagnetic field. This magnetic field try to magnetize the iron piece, and it is also becomes a magnet. Now, so for example, North Pole and South Pole, they try to drag towards the coil. Once it try to move this direction, but spring is unable to allow to move this direction. So that means the spring is created the controlling torque. This magnetic field, the current which is produces the field, that is developed the deflecting torque. Once the deflecting torque is equal to controlling torque, two forces are torques are equal, at that condition the pointer will stable here. It is moved from this position to this position. So this is our reading. For example, this is 0.2 amperes. that is the current which is flowing in the coil. We are going to calibrate it. If the current value increased from 0.2 amperes to 0.5 amperes, then what will happen? Automatically the flux increases, then the pulls towards the inside. Then when TD increases, it try to move furthermore, then pointer will come to here. At that wherever the equilibrium takes place, TD is equal to TC, then it will stop. Then that is the reading, that is the 5 amperes. If further increases current 0.8 amperes, the flux further increases, the TD increases further, then it will try to move this direction. So this is the reading. That means go on increasing the current in the coil. So movement of the iron piece towards the coil also moved on a calibrated scale. If less current, less movement, more current, more movement. This principle. So that means this is a attraction type instrument. This principle we are using in our moving iron attraction type instruments. Okay. So this is the basic thing. Now you can see arrangement. So what is the arrangement in our, that is the basic things we have seen in school levels. Now that same principle, arranging as per our requirement with different materials. What it has? What it is, the electromagnet, it has the iron piece, we can say the vane, it is pivoted here, and there is a spindle provided, and there is a air friction damping, and this weight is provided, gravity weight. Okay. This is produced by the controlling torque, this is produced with the damping torque, and this is produced the, this is a deflecting torque. The coil is going to produce a deflecting torque, this is producing the damping torque, then the weight is going to produce the controlling torque. Everything is satisfied. Now the coil is placed here, and initially this is placed, for example, initially what will happen? Initially it will in this position, and the pointer may be this direction. It is a calibrated scale. Okay, you can see it. So initially this is maybe this position. So the iron piece vane may be this position. Now then pointer may be this position and calibrated scale. Now what will happen? Once supply is given, coil, it establishes a magnetic field, then try to attract the iron piece towards this direction. Once it is tried to move the iron piece, the spindle is attached to the iron piece, that will tilt, that is a move one direction. Then pointer also moved from this direction to this direction, that some angle is taken place here. Okay. So this is the basic idea. So a deflecting torque depend upon what factors? Say a deflecting torque is based on the attraction wave. So here what is happen? That is equal, a depend on the current I. So deflecting torque produced by the current. If current is more, deflecting torque is more. At the same time, so it should be magnetized, this iron piece also. That means here what is the force? The force of attraction is directly proportional to the magnetic field of the coil, that is the M1. At the same time, the magnetic field of the iron piece, magnetized field, try to attack M2. So that means M1 also depend on the current and M2 also depend on the current, because if strong current is more magnetic field, if the more magnetic field, so at the same time it also strong magnet, it becomes also iron piece also strong, so magnetized material. So this magnetization of this iron piece and electromagnet of this coil plays a vital role of Td. So, now the force is equal to, so that is directly proportional to the magnetic current in the coil and magnetized iron piece. So, that is equal F is directly proportional to the I square of the current. That means here, so instead of force we are going to the force into displacement is the torque. Now, torque is equal to this one. Now, whatever the torque is developed in this case, so the T torque is directly proportional to the I square. That means the deflecting torque is directly proportional to the square of the current. In previous cases, we have seen the deflecting torque is directly proportional to the only current, because at that condition we used, and here we use the one permanent magnet. It is a stable, it does not change, it is constant value, and coil is a electromagnet that is dependent on the current. Now, in this case, so both are dependent upon the input current. If more current, more magnetic coil and more magnetized iron piece. That is why, so Td is equal directly proportional to the I square. Okay. Now, this is the basic thing. Now, working, you can see the one animation, how this oval shaped iron piece is attracted when current is passing through the coil. You can see the coil red color, at that condition the current is flowing, then there is a magnetic field is developed, then the green color pivot, that is the oval shaped iron piece, is attracted. Due to this one, this pointer is moved from 10 to 60 value, you can see on this one. Okay. So, this is the operation of moving iron instrument attraction type. It is attracted towards the inside the solenoid. Okay. Now, let us see the salient points what you have seen up to. If the current reverses in the coil establishes a magnetism in opposite direction. Same here we can see what will happen. Here the current is flowing here, is leaving here. It produces the flux. So, this try to, one for example, this is a north pole, this is a south pole. Similarly, it is a magnetized, it try to attract this is an iron piece, try will attract whether the north pole or south pole, try to iron because of magnetic material, ferromagnetic material. Iron piece is always attracted towards the magnet. So, now north pole will try to attract the iron piece. In second case, for example, if the current entering here and leaving this coil, now what will happen? Current direction changes. Even then what will happen? There is a magnetic field. Now, south and north is developed in the magnetic field. The south pole also try to attract the iron piece. So, that means if the current reverses in the coil establishes a magnetism in opposite direction. Okay. Now, also the iron is attracted inside the coil, whether this direction or that direction, but it establishes a magnetic field. The magnetic field try to attract the whether north pole and south pole on iron piece towards it. The deflection torque remains same. Td is equal same whether it is a north pole to south pole or south pole to north pole. The force of instrument can be used for, so this instrument can be used for, that's why, so either direction it is gives a deflection on a same direction. So, it can be used for AC as well as the DC measurements, whether voltage or current. Okay. And at final deflection at equilibrium, we have seen the deflecting torque equal to the controlling torque. So, at that condition what happened? So, Td is equal to Tc, and therefore, that scale is stable condition at that condition, both are equal. scale is not uniform because the TD is directly proportional to the square of the current. It is a non-linear value. So, why it is not uniform? Because, for example, you take the one example. When 1 ampere is given in the coil, suppose here given the current, you can change the current direction. Okay, 1 here coil is given. Okay, 1 ampere current is given to my coil. It try to attract the iron piece inside. Then it moves from 0 to some angle of theta. The theta may be, for example, 5 degrees. That means at initially I applied 1 ampere of current. There is a deflection of pointer. It moves on a calibrated scale. If I measure the angle from 0 to this position, then let us assume that is the angle is called 5 degrees deflection. Now the current is increased to the 2 amperes. As you know that it becomes a strong magnet, it try to attract further inside. Then the deflection will try to move the furthermore. At that condition 2 amperes. Then what will happen? So, what is the angle? Now, we know that. So, at the TD is equal TC, we know that. So, what is the formula? Already we have seen, that is equal TD is directly proportional to the square of the current. So, now here what is happened? So, I is equal to how much? 2 amperes, 2 whole square. For 1 ampere 5 degrees and now 2. So, that is equal to 5 degrees into square of the current, that is equal 2 whole square 4. That means 4 5 is a 20. Now, we are going to get this 20 degrees deflection. You can see from 0 to 1 we are 5 degrees and 1 to 2 difference is of only 1, 0 to 1 difference 5 degrees, 1 to 2 amperes the difference is of 1 ampere, but deflection is 20 degrees. For example, 3 amperes I am going to allow. What will happen? The 5 degrees into 3 is a 9, 3 square 9, 9 is a 45. Now, the angle is going to 45 degrees. You can see it. So, what is the distance between the 5 degrees to 20 degrees? What is the distance between 20 to 45 degrees? It is a uniform. You can see, let us. So, for example, you take the one graph here. So, this is called 0. For example, 5, 10 degrees. For example, 5 degrees, 10 degrees, 20 degrees and 30 degrees and 40 degrees, for example. The point is here. 1 ampere is applied, it is moved from, so here you can see it, moved from 0 to 5 amperes. Now we have seen the angle is equal to how much? 5 degrees. Now 2 amperes we are going to get the 20 degrees. That means, so for 1 ampere from 0 to 1 ampere it is moved this amount of the arc length, or is called altimeter. So, this is the distance angle. Now, in 2 amperes it is going to the 20, you can see this. So, this angle is equal to how much? Is 20 degrees. Now, you can see the length from this to this 20. Now, 3 amperes, then what will happen? It is going to the 45. So, from this one it is going to the 45. Now, see the angle, the arc also increased. That means, it is only 1 ampere between this and 2. Here also only 1 ampere, here also only 1 ampere, but angle is changing. Angle is 5 degrees, angle is 20 degrees, angle is 45 degrees, go on. That means, the scale is not uniform in this case. You can see the arc. This arc is length is less, the arc is more, is further more. That means, once the current increases, so the arc length is changing, scale is not uniform. So this instrument is known as the cramped at starting and cramped at ending. So whereas in case of moving coil instruments, so every degree uniform, that means in MC instruments we are going to get it. What is that one? So in MC instruments, now here, so what is this one? So for example, this is a 1 ampere and 2 amperes and 3 amperes and 4 amperes. So distance between these two distance is a uniform and equal. But whereas in MI instruments, the arc length may not be equal in case of MI instruments. So MC instruments are a uniform scale, MI instruments are non-uniform scale due to the, so here MC instruments is TD is directly proportional to theta, whereas this the TD is directly to theta, that is directly to current. So here MI instruments, the TD is directly proportional to the square of the current or theta square. That's why scale is not uniform. Okay. So now therefore the scale is when TD is equal to TC, that's one. And next, scale is not uniform, and when the instrument is connected to AC supply, it indicates the RMS value. Okay. So root mean square value will shows directly. So because here it can be used AC as well as a DC. So where TD is equal to square of the current. For example, if you are taking the average of TD proportional to the time average of I square, we are going to, that is called theta proportional to I square RMS. I think it's no need of for diploma level. Okay. So theta is directly proportional to the, here what is the formula? Here, so we know that TD is directly proportional to the I square, but here average torque developed, deflection torque is equal to average TD is directly proportional to the time average of I square. So here, so we can write it, so this is nothing but theta is directly proportional to the time average, we can write it, so RMS value, so I square RMS. That means the angle is directly proportional to the RMS value. That means whatever the reading shown by the MI instrument is the root mean square value. Now this we have seen. Okay. Any doubts? Just what is the construction, what are the parts of a attraction type instruments, and how, what are the each part purpose, and how it works at equilibrium, what is the happened you have seen. Now coming to the another that one, that's now repulsion type. Now previously we have seen the north pole, opposite poles is created, iron piece is placed, iron can be attracted with the north pole and south pole. Now here we are going to is the repulsion force for repulsion at instruments. Let us see it. Here repulsion type, moving iron instrument. So what do you mean by this repulsion? So repulsion, here you can see it. So there is a coil similar to that wire coil, so through which the current is passing. It is a cylindrical one. You can see the top side plan, you are going to this one. Now this is connected to the spindle. Now you can see the spindle. Spindle is attached to the our controlling torque, at the same time pointer, and it is on the calibrated scale similar to the everything. Now what is the difference here? Here one difference, what is, you can observe it. Now here what will happen? So this outer side is the coil, this coil on which there is a winding wound on it, and here the center is the spindle, this is spindle. Between the spindle attached to the one iron piece here, you can see, observe it. Okay, one iron piece attached here is the spindle, and spindle is attached to the one iron piece here, and is connected to the pointer. This spindle is placed here, and attached to this one, and it's kind of the one iron piece is placed here. This you can see inside. At the same time, and one another iron piece also is attached here. You can see this is the one. Okay, so this is a iron piece. This one color you can change it. Now you can see this is a one iron piece. Okay, that attached to the this electromagnet. Now another piece that is attached to the spindle, this spindle which is attached to the one iron piece. So that is attached to the, this is a place run similar to the jewelry bearings and both sides, and connected the spring control, so everything. Now here you are going to remember is the spindle another connected to the one iron piece. This iron piece you can observe here, this one. Here is the one iron piece, here is the another iron piece, both are placed side by side, small air gap between this. Now whenever the supply is given to this coil, what will happen? There is a strong magnetic field flux developed inside the flux. Now around these two iron pieces there is a strong magnetic field. Due to the magnetic field, this iron piece magnetized, this iron piece also magnetized, because both are placed in parallel and the same magnetic field. Due to the nature, and now let us assume, so these two magnets, so now this iron piece act as a north pole and this act as a south pole, because both are placed in the same magnetic, it is also act as the north pole, it acts as a south pole, because both pieces are parallel each other, same magnetic field. Now but what happened? So one, it is connected to the body, this is the body, it is connected to the strong body. Now it is placed connected to the on spindle, placed on bearings. Now what happened? So once two iron pieces are magnetized, then north pole and north pole, as per the Coulombs law, north pole and north pole like poles repel each other. Then so both are repel each other, but this piece is attached to the stationary part, body part, rigid, whereas this piece is attached to the spindle which is placed on a jeweled bearings, e.g. to it is a rotor. Due to the repulsion force, it will move the iron piece which is attached to the spindle will move. Once spindle is moved, our pointer also moves on this calibrated scale. If current is more force, repulsion force, and more movement of the pointer. Here also what is happened? Here two magnets, so deflecting torque, the deflecting torque, here you can see deflecting torque TD is directly proportional to the what is the flux of this one, what is the flux of this one. Okay, two, between the two, one stationary, one is the movement. So this depend upon this magnetic field, that is depend upon the current, that is equal I, and this also depend upon the magnetic field, that is also depend upon the current. So that is called I into I. So that is called I square. Here also scale is not uniform. So when TD, deflecting torque, is equal to the TC at equilibrium, then what is happened? Then the theta is directly proportional to the I square. So here what has happened? The scale is not uniform. Previously we have seen theta is equal to, so for 1 ampere we are going to get the 5 degrees, 2 amperes we are going to the 20 degrees, and 3 amperes we are going to the 45 degrees. Scale is not uniform. Similarly here also the iron pieces magnetized due to the same magnetic field, that is depend upon the current. So due to this current, there is a deflection torque is developed. The deflection torque is directly proportional to the square of the current. Hence the scale which is used in our moving iron repulsion type or attraction type scale is not uniform. Okay. So, now this is the overall idea. So, let us see in details. Now, construction of repulsion type MI instruments. Here same thing, you can see this is a coil, electromagnetic coil, this is the coil, and on which there is a winding is wound, the power is coming here, entering and leaving, this is a coil. Now, next here is the one spindle is provided, one spindle is provided here. Okay, this is a spindle. A spindle is placed on jewelry bearings as usual, placed on jewelry bearings, and it attached to the one iron piece. You can see this is attached to the one iron piece, this one iron piece to the spindle. Okay, one spindle iron piece. This you can see that this shape iron piece is attached here. Here. Now, another iron piece also provided here, the fixed iron piece attached to the this body, and another piece also attached to the here, attached to this one. You can see it, fixed iron and spindle iron. This is a moving iron is placed side by side. You can see this is a side by side. Once again you can see it. So, what you are going to observe, there is a spindle, there is a iron piece, and another iron piece is connected to the coil. Okay, this is connected to the coil. Now, it is a stationary, this is the placed on bearings, rotor. Okay, you can see in the side. Now, coming to this one, spring control is provided here, controlling torque, and fluid friction damping is provided here, and our spindle attached to the our pointer, and pointer is on a calibrated scale, same measurements. Okay, this is a construction. The consists of a fixed hollow cylindrical coil. Inside the coil, two soft iron rods or vanes, we can say vein, or parallel to each other and parallel to axis are placed. One iron vein is fixed to the coil and another iron vein is fixed to the spindle, moving iron. A pointer is attached to the spindle. The spindle is free to rotate inside the coil. Spring control is provided and air friction is provided, or any type of the damping torque we are going to provide. Okay. So, this is a, I think what is the term? Okay, no problem. So, basic principles. I think you very familiar about this one, but you can see, just recall what you have seen in previous classes in school level. Here is the iron piece, one iron piece. This is the iron piece, just is a ferromagnetic material. Now, this is our solenoid. This is a copper wire, wound it. Now, you can see it. Now, when the current is passing through this one and there is a magnetic field develops and it is going to the element. Once two iron pieces nearby here, so there is a magnetic field develop around this coil, in which this magnet one iron piece is placed side by side in parallel. Now, due to the magnetization of these iron pieces act as magnets. Due to this one, for example, here north pole and north pole one side and another side, and the south pole may be established. Let us assume. During this process, like poles repel each other. So, this repel each other. This pole, this will try this direction, this will goes this direction. At the same time, this direction. That means both are repel each other. Okay. So, due to this one, what will there is a repulsive force is developed. So, when current is increased furthermore, more deflection, more repulsive force, more movement of the coil. For example, I place this is connected to the fixed one, then automatically it will move the one direction. If it connected to the one spindle or one pointer here, the pointer will move on this one. First we have seen. If moves more refraction, it will go some more direction. So, based on this one, pointer also move on a calibrated scale. So, how much current flowing in the coil depends on this movement of the pointer on a calibrated scale. That indicates that is the value of the current which is flowing in the coil. Okay. Now, this you can see the operation. What is happened? Here also same thing, same current is flowing, and this arrangements, the spindle you can see what are the parts. This is a coil, and the spindle is, you can observe the spindle and attached to the pointer, and there is a spring control provision is provided, and there is a 2 iron pieces inside, you can see it. Here is one iron piece, another iron piece is attached to this one, attached to this one. Okay. So, here the force of attraction, both coils are, so force is equal as per the Coulombs law, the force is the magnitude of the one iron piece or magnitude of the other iron piece, magnetized iron pieces. The force directly proportional to the M1 and M2, and that is dependent on the, so the square of that one, then we are going to F is force of directly proportional to the square of the current, because the both iron pieces depend upon the magnetic field, that magnetic field is dependent upon our current. So, that is why the force is directly proportional to the I square, you can see here I square. Now, here when the TD is directed, developed torque, that is a deflecting torque is proportional to the square of the current. But whereas we are using the spring control, the TC is directly proportional to the theta only. So, under equilibrium condition, deflecting torque is equal to controlling torque. At that condition, the theta is directly proportional to the square of the current. So, once again it is a non-linear. Scale is non-linear. It is a cramped at starting and ending. Okay. Now, salient points. When the current through the coil is 0, what is happen? The pointer in the initial position showing 0 only. No magnetized iron pieces inside the coil. No repulsive force arised. The fixed and moving irons are close to each other, just air gap. When operating current is passing through the coil, it produces a magnetic field inside the coil. 2 vanes within the coil are magnetized similarly, same polarity, north pole, one side north pole and south pole. So, you can see here, one is attached to here and one is attached to this spindle, A and B, you can see it. Okay, fixed iron and moving iron. A is the fixed one, B is the attached to the spindle. Hence, 2 magnets repel each other, like poles are repel each other. The mobile vane is mounted on the spindle, moves away from the fixed vane. So, try to move. The movement of the moving iron depends on the strength of the current through the coil, the current coil. The pointer moves on a graduated scale along with a spindle. Thus, the current flowing through the coil can be read directly on the deflection. Okay. So, this is the basic principle of repulsion type moving iron instruments. Now, how to identify whether the instrument in laboratory is moving iron or moving coil? So, moving coil instruments, we have seen that it can be used as a altimeter and ammeter. Similarly, moving iron instruments can be used as a altimeter and a ammeter. The physical point of view, both are same size. While you are doing the experiment in our electrical laboratory, instead of you are going to use the AC supply, if you are connected to the MC coil, the moving coil instrument, there is a problem may be occurred. Sometimes it may be burnout. If MI instruments can be used for AC and DC, instead of you are going to use it DC, nothing will happen, but accurate reading may not be get as comparing to the moving coil instrument. But same machine, if you are using AC, the moving coil may not be shows any reading. So you have to remember that thing. Sir, how to know this one, whether this instrument is a moving iron or moving coil? So that purpose we are going to remember as electrical students. We are going to perform the experiments in diploma level and BTech level. So as we know that first indication is that in case of the moving coil instruments, the deflecting torque is directly proportional to the theta. The theta directly proportional to the current. That means scale is uniform. Scale is uniform. Uniformly, the arc is the length of the arc is uniform in case of the moving coil instruments. Scale is uniform. Whereas in moving iron instruments, we have seen that theta is directly proportional to the square of the current, the non-linear. At starting and ending, the angle is very less, and middle is changing. So scale, that is a scale at starting is cramped and ending also cramped. As we know that at 1 amperes we are going to get the 5 degrees. For the same 1 amperes we are going to the 20 degrees. For the same 1 ampere we are going to the 45 degrees. The arc is, the length of the arc is changing. So by seeing this one, whether the scale is uniform or cramped, we can say that okay, scale is uniform. It is a MC, moving iron instruments. The scale is not uniform, then we can say this is a moving iron instruments. This thing you have to remember while handling our instruments. Another thing also you have to remember that if you are observing inside of the panel of meter, you are going to observe small indications of the U-shaped magnet or shoe magnet. So that indicates that permanent magnet. The permanent magnet can be used only for moving coil instruments. So we can use it only for DC purpose. Otherwise, there is a zigzag line or iron piece. There is a signal on sine wave. Then we can easily understand that it is a moving iron instrument. At the same time, sometimes we can observe in our laboratory also in moving coil instruments there is a indication of plus and minus sign on the meter. Sometimes it indicates a red color and black color, plus and minus, whereas moving iron instruments no plus and minus business. So this is also one thing you have to remember. Okay, so let us see here. The scale is cramped at starting at ending of the moving iron instruments. What do you mean the cramped? You can see it practically. So this is a one real meter. What is the meter? This one, the voltmeter maybe. So here what will happen? 0 to 100 volts gap between this one. You can see the what is the arc length. 100 to 200 what arc length. What is the 200 to 300? What is this one? Once again is reducing. That means here small increase, small. That means here what is happen? Starting small. Here is the changes. So there we can see the cramped. Scale is cramped, not uniform. Okay, by seeing this one you are going to observe that okay, this is the MI instrument. If you are unable to identify this scale due to your something sight eyesight, then you can see, observe that here is another indication. There is, you can see this is one coil and on which there is iron piece, you can see here. Then by this we are going to understand that it is a moving iron instruments. Iron piece is placed in a coil, so it is a moving iron instruments. By seeing this one, we can easily identify the moving iron instruments in our laboratory. Okay. And you can see this same thing here explained is the AC indication. That is the AC indication. If you are observing here, sometimes we are going to see that scale also it indicates that is the AC. If you are using the AC and DC, this is a MI, and whereas only it can be a horseshoe magnet, so we can use for the DC only. Okay. So this is identification of instruments, because it is a very essential of as electrical students to know the difference between the MI and the MC instruments. Now you can see the different of the instruments. These instruments also so different. So it may be different physical shapes, but you have to remember by seeing the scale you can going to observe. Okay, that is here also everything you can see it. So here also scale you can observe it. Scale you can see it here, the gap. Sometimes there is no readings also, left some the blank, based on the you are going to assume the scale distance. Okay, so this is you can see the distance between the 2 points. Here the scale is difference, here is where is distance, small distance. Okay. Now here also you can see it. Now what are the advantages of attraction type instruments, whether the repulsion or attraction moving coil instruments? So because comparing to the MC instruments, the moving iron instruments are, you can say it's not attraction, it may be advantage the moving iron instruments. It is a very cheap and best. Okay, cheap and best. It should be rugged and robust and reasonable accuracy, and simple in operation and simple in construction, and high operating torque and momentarily overload capacity it can withstand if 20% exceed the load current also. Okay, used for AC and DC. This is the beauty of the moving iron instruments, whereas moving coil instruments can be used only for DC. But in this case we are going to use the AC and DC. It is a perfect reading in AC, but comparing to the moving coil instruments, it may not give the as much as accurate of moving coil instruments, but it will give the DC value also. Okay, so these are some advantages of moving iron instruments. Now what are the disadvantages? So disadvantages are scale is not uniform. What is happened? So initially the scale is such that initially some this one, and here 0, 1, 2, 3. So what has happened? So there is no readings here. Here is a one dials pointers. So here there is no this small points indications. So you have to guess it what is the value, and this length also very small. You can observe here also. So you can see the digits here. So there is a possible to confuse the observation time. There is a possible to error. Next, the power consumption is more. In this case, we require the strong magnetic field to attract inside as well as magnetize the two iron pieces. So more current is required. And errors are induced due to the hysteresis and stray magnetic fields. So here hysteresis means so due to the magnetic materials. So if you are using the silicon materials, we are going to avoid the hysteresis somewhat, and it may be subjected to the other magnets which is placed side by our meter. This magnetic field may be affect the our meter reading. So we have to conceal such a that it avoid the external magnetic field. Otherwise, you have to remove the all nearby magnetic materials. Otherwise, that disturbs to the our readings. Errors are also induced due to the change of frequency in case of AC. If AC changes, then what will happen? So we know that what is the formula? So magnetic field. So L is omega L is equal to 2 phi FL. So that is equal to, so here the flux, the inductive valves XL, that is equal XL. Due to the XL, there is a magnetic field. So frequency changes, this value changed. Then there is a possible to error. Whereas DC, the frequency is equal how much? 0. Now, when the instrument is connected across the supply, the current proportional to the voltage flows through the coil. So this instrument, if you are used as a voltmeter, similar to the moving coil instruments. So these moving iron instruments can be used as a voltmeter and ammeter. Now the working of the moving coil instruments as a voltmeter. When the instrument is connected across the supply, the current proportional to the voltage flows through the coil. The flux produced inside the coil attracts the oval shaped moving iron. As a result, the moving vane moves inside the coil. Voltmeter connected, as you know that the basics already we have seen last class. So how we are going to connect the voltmeter? You remember that always voltmeter should be connected in parallel with the supply, or where you are going to find the difference between the two nodes, junctions. At that condition you are going to connect it. Okay, voltmeter connected across the supply and across the load. So here, so I want to know that what is the voltage drop across the bulb. So I connected the our MI instrument here. Okay, can you tell that? So whether what is the voltage? For example, voltage is a 20 volts is applied here. What is the voltage across this one? Whether it is a 20 volts or less than 20 volts. Always less than 20 volts, because some of the voltage drop may be occurred here. So the 20 volts may be, for example, 5 volts, 15 volts here. So whether it's 15 or 16 or 20, so can be measured with help of our meter. That's why I connected across this one. If you are placing, this is a variac. By changing the variac, we are going to get the different voltage across the bulb. Then intensity of the bulb also changes. Just like if you are, instead of bulb, you are connected to the fan, regulator fan. This is a regulator, this is a fan, ceiling fan. So by changing the knobs, so 1, 2, 3, 4, 5, so we are going to get the speed of the fan. Similarly, so I want to know that, so at first note, step 1, if the fan is running at a speed, low speed, then what is the voltage across the fan? I am going to find with help of the voltmeter if I connected across the two terminals. If I place the second knob, then speed will increase the fan. Then at that condition, what is the voltage? The third, what is the voltage? Fourth, what is the voltage? Fifth, what is the voltage? Same at fifth, whatever the input voltage, that voltage applied across the fifth. There is no the resistance in series to the load. That is simple circuit we are going to do in laboratories. Okay, so this connect, the voltmeter can be used to measure the voltage across two nodes. Here the one node, second node. Now when the instrument is connected in series with the supply, the load current flows through the coil. Then it acts as an ammeter. The working of MI type instruments as an ammeter. So same instrument can be used as an ammeter. So when the instrument is connected in series with the supply, the load current flows through the current. Whatever the current taken by this load, same current is flowing through the ammeter. So in case of ammeter, the resistance should be very, very low. Hence we connected with the load in series only. Whereas previous case, voltmeter has the high resistance values. Now the flux produced inside the coil attracts the oval shaped moving iron inside the coil. As a result, the moving vane moves inside the coil. Okay, so how we are going to connect the ammeter? The ammeter connected in series with the supply. Now we can see it. This is connected, same here the ammeter is connected here in series. The supply, this is the load. Okay. So, based on the load, what is the current will? The current is entering, so that produces the flux that attract the oval shaped iron piece, or there is a repulsion force between the two vanes. Okay. So, this is the thing. So, these are the MI type instruments we are going to use, whether it is a voltmeter and ammeter. So, how we are going to extend the voltmeter? For the higher ranges, we are going to connect the high resistance in series. So, we can say that is the multiplier. By connecting the multiplier in series to the given instrument, so we can measure the high range of the voltage. And if you are using the as a ammeter, MI instruments ammeter, how we are going to measure the large amount of the current? By connecting the shunt material. Shunt. So, shunt is used to enhance the range of the ammeters. So, previous class we have seen that the constant and material are used as a shunt as well as the multiplier. So, that means the temperature coefficient of this one is a constant. It does not change with change in temperature. Okay. So, dear students, now I think the time is more. Now, you can see the one practical instrument. This is an opened moving iron instrument. You can see this is a fluid friction damping purpose, and we taken out the one pointer, and is a adjusting pointer purpose. You can see it. There is a fixed the cylinder type iron piece. If you remove that one, there is a coil is present inside. So, you can see the coil, that's other side. Now, you can see it. This is the coil connected here. Okay. And this spindle with the pointer and some vane inside is connected, fixed vane and moving vane. Here you can see this that is connected the two vanes, the repulsion type. This you can see the one vane, okay, shaped vane. You can see inside also there is a vane which is attached to the spindle. The spindle, you can see it. Yes, you are going to see the one vane. It is attached to the spindle. If the spindle is moving, the attached iron piece also moving. You can see it. Okay, now you can see it. Okay, so just moving. So this and previous, that is both are parallel each other. Now inside you can see the spring. The spring you can see for the controlling purpose, control torque we are going to use it. You can see spring, you can see it is trying to show it, that courtesy to that person who is going to practically showing us. Okay. So, another video, another. So, working principle, and already we have seen, just you can see what is the structure of moving iron meters. So, when supply is given, it magnetized. You can see the animation also, color is changing. It is a fixed vane and moving vane inside, and a hairspring controlling torque, and a pointer and non-linear scale is placed. You can see. So, inside there is a plan, you can see it, coil, outside is a coil, and there is a two vanes, one fixed vane and moving vane is attached. So, you can see how it is changing, plan and this one. The spindle move at the time of the movement, it is moving the vanes. When controlling torque equal to the deflecting torque, the vane will spindle will stop to moving. Okay, it is moving on a calibrated scale. A good animation. This is also courtesy to that person. What are the advantages, disadvantages? Already we have seen. So, moving iron instruments measured DC as well as AC, and it is a non-linear scale. And measuring AC DC moving iron instruments. Okay, no need this one. Okay, Let us summarize what you have seen. You can observe the plenty number of videos on animation and moving iron instruments, all instruments. Now, let us summarize. In this period, we have discussed the types of moving iron instruments, and at the same time, we have done one problem based on the moving coil instrument also, and construction of attraction type moving iron instruments, and working of attraction type moving iron instruments, and working of attraction type moving iron instruments as a voltmeter and ammeter. Similarly, we have seen the construction and working principle of the repulsion type moving iron instruments, and its act as a voltmeter and ammeter. Okay, so these are the some topics used learned in this class. So if you any doubts, please ask in the next class. Thank you for listening.